Is okay, that what have we done until now? Okay, so we have studied that to specify, to describe motion, it's important to consider something called the position vector, and then you can talk about how fast this position vector is changing. That gives you another vector called the velocity vector, and if you look at how fast this is changing, that gives you another vector called the acceleration vector. Okay, so until now we have basically been focused on studying, for example, the motion of one object, or maybe two objects or three objects, using these mathematical tools. Okay. Now there's a complication to this story that I need to tell you about today. The complication is simply that you ask, okay, that these vectors are according to who? Who is performing these measurements? So the first thing that you have to realize is that the position vector, the velocity vector, the acceleration vector, whatever measurements you are doing are always with respect to some observer. They are always with respect to somebody who is performing the measurements. And different observers can can find different results when they measure the same thing. So for example, if you look to the seat to the left of you, the position vector of that person, if there is indeed a person sitting, if there isn't, imagine that there is a person sitting, that position vector, of course, for you, for that person, is a very small vector. For me, the position vector for the same person is a pretty big vector. We are both correct, of course, because we are both describing the position of the same object, but from different viewpoints. Okay, so these position vectors always with respect to some coordinate system, or if you want to visualize it physically, with respect to some observer who's performing the measurements. If the position vectors depend on the observer, maybe the velocity vector also does, maybe the acceleration vector also does. Okay, so different observers can measure different velocity vectors for the same object, and it's important that you learn how to connect these measurements with each other. That's basically the topic of today's lecture. How do you connect the velocity measurements of one observer with the velocity measurements of another observer? How do you connect the acceleration measurements of one observer with the acceleration measurements of some other observer of the same object? Okay, so the both observers are measuring the same object. Okay, and how do you connect the position vector as measured by one observer to the position vector as measured by another observer of the same object? Okay, why are we doing this? Of course, why are we even doing mechanics? Okay, but why are we doing this? The three questions I posed essentially, that how are these vectors related to each other according to two different observers, is because essentially you later on, when in the next lecture when we start talking about Newton's laws, you realize that these relationships are of critical importance before you even start talking about Newton's laws. Okay, so you can only really start talking about Newton's laws once you understand how measurements connect with each other. Okay, so how measurements for different observers, how are they related to each other? Okay, because the basic question is that, okay, if you have Newton's second law, and that is F is equal to ma, right? But A according to who? M according to who? F according to who? Who's performing the measurements? As in, are all observers equally eligible to use Newton's second law, or can Newton's second law only be used for some special observers? It turns out that actually, surprisingly for you, is the second. Only some special observers can apply Newton's second law. Not everybody can apply Newton's second law. Okay, and to understand that, you need to first of all understand how are these vectors related from one observer to another observer. Okay, on the face of it, these are very simple, commonplace questions. You are traveling in a car, there is a book stationary right next to you, and the car is moving. You will say, of course, that the velocity of the book is 0. But somebody standing outside on the road will say that the velocity of the book is non-zero. Both of you are correct, of course. And of course, in this case, the relationship between the velocity of the book as measured by you, and the velocity of the book as measured by somebody outside the car is very simple. It's just essentially you just add in the velocity of the car. Okay, but in many cases, in other cases, it may not be that simple. It may not be just a simple addition. Okay. Okay, so how is the position vector of an object as measured by one observer related to the position vector of the same object as measured by another observer? Okay, so you have an object P and you have an observer, my favorite stick figure, A. A wants to measure the position of this object P. What does he do? Of course, he says that, okay, I am the origin of my coordinate system. Essentially, I am going to measure positions of whatever object I am interested in with respect to my own position. Essentially, observer is just a physical picture of a coordinate system. If you want to visualize this abstractly, there is a coordinate system over here with origin over here. And with respect to this origin, you are measuring the position of this object P. So basically, you have a vector like that. This is a position vector. So let's call it R. You have another observer. Right now, just to begin, just imagine that these two observers are on a train station, stationary with respect to each other. Simplest scenario. They are just spatially separated, so they are not hugging each other or whatever. Okay, okay, I don't judge. So you have that. Okay, so they just stationary with respect to each other, some distance away. Social distancing, you know, okay. So, but they are stationary with respect to each other. That's the important point. Okay, because very soon I'll make B run. Okay, I'll make this observer start running or doing whatever. Okay, again I don't judge. Okay, but jo bhi karna cha rahe ho kare. Okay, so you have B. Okay, so you have this observer. Of course, this observer also. आपको क्या बेवकूफ लोग हैं जो एक ऑब्जेक्ट के मोशन में इतना इंटरेस्टेड है, but this observer, believe it or not, is also interested in the motion of P. Okay, you don't know what P is, so that might be a very very valid question. Okay, so anyway, you have that observer, of course, has this as the position vector, and you say that this is R, and of course this is immediately very bad notation, because you are using the same symbol to represent two very different vectors. They are different vectors. Both are position vectors, of course. There is this vector and then there is this vector, right? But you are using the same symbol. So you have to distinguish between these two vectors. The convention that I'll follow is that you put in subscript two things. You put in your subscript the property of which object, and then you put in who's doing the measurement. So here this is the position vector of object P according to, so you put in PA. Some books follow the opposite convention. So they will put in the first subscript will denote who's performing the measurement, and then the second subscript will denote measurement of what. Okay, so be careful if you're using multiple books with infinitesimal probability that is happening, but still, you know, umeed pe duniya zinda hai. Okay, just be careful. Okay, because RAP is the exact opposite vector of RPA. RAP would be the position vector of object A now as measured by an observer on P. So that would be the exact opposite vector. Okay, and this would be PB. Okay, and then of course you can draw another position vector that basically joins these two observers. This would be R. The way I have drawn it, students commonly ask, आपको कैसे पता इस तरफ arrow बनाना? वो बना लो यार, उल्टा बना लो. Okay, it doesn't matter. Okay, as long as you're consistent in whatever you're doing after that, you can draw these arrows in any direction that you like. But usually, of course, you usually try to point two of your arrows towards the object in whose motion you are interested in. Okay, normally, for example, if this is a ball that is going up, you wouldn't really be interested. You would really be interested in the motion of the ball, not the motion of these observers. Of course, if ball is going up, the ball will say no, an observer on the ball would say that I am stationary, is these guys who are moving. Okay, so it depends on your frame of reference. Okay, anyway, so this is RBA, right? Okay, and from this diagram, okay, this object P is moving. So what is going on is that basically you have made a movie of this situation and you have paused your movie, and this is basically what you're seeing in your movie without these arrows, of course. Those arrows I put in. Okay, so this is a still shot from the movie. As you unpause the movie, what happens? What happens with these arrows? This arrow doesn't change because I'm assuming that B and A are stationary. Again, you know, I mean, I can only push language so far, but you can always ask you stationary with respect to who? Well, stationary with respect to the train station. Okay, as in another observer on the train station say that velocity of these two guys is 0. Okay, so anyway, so these two arrows, however, will change with time. That's exactly what we say, that the object is moving. Moving according to who? Moving according to A, and B will also say that the object is moving. Okay. So as the object moves, of course, these arrows do change. So for example, some instant of time later, you have this situation. This arrow doesn't change. So now you have that this arrow, and you have this arrow, and you have this arrow. Notice that at the original time, I can write down RBA at time t plus, RBA to depend नहीं कर रहा time पे, RBA plus RPB at time t equals RPA at time t. Very simply put, this white arrow plus this white arrow equals this white arrow. Sometime later, this white arrow plus this yellow arrow equals this yellow arrow. Sure, the position vectors did change. But the relationship between them always remains this. As the object moves, the arrows change, but you can always form essentially this triangle of arrows. Okay, so you have this that is true at any time t. Okay, right? Okay, so what you have then is that yes, the position vectors do depend on which observer you are talking about, but what about the displacement vectors? What's the displacement vector of the object as it moves from here to here according to A? A क्या बनाएगा displacement vector?
Yellow line minus white line.
Essentially yellow minus this, you would draw this. And what would B draw as the displacement vector?
B का yellow minus B का white.
This plus this, that would be exactly the same arrow. The displacement vector will be the same for both observers. But that's only true because the two observers are stationary with respect to each other. Okay? In other words, if agar aap stationary ho, right, on a train station, there's another person over there stationary, there's a third person over there who takes one step to the right. Both of you will agree that that person took one step to the right. Okay, there's nothing very weird about that. Okay, but again, you need to be able to translate these simple scenarios into how you describe them mathematically. Okay, anyway, right. So displacement vectors are the same for both observers, but again, that is only true because both observers are not moving with respect to each other. Now suppose that B gets on the train. और ट्रेन के बाहर भी कुछ हो रहा है. Okay, there's a ball that is being thrown outside the train. Okay, so you have this ball that is going up. For example, एक बंदा ट्रेन स्टेशन से देख रहा है उसी बॉल को, एक बंदा मूविंग ट्रेन से देख रहा है उसी बॉल को. And now they are both looking at the motion of this moving ball. So now this B is also moving with respect to A. Of course, with respect to B, B कहेगा मैं स्टेशनरी हूं, A मूव कर रहा है. Okay, so B is moving with respect to A. That means that this position vector is also dependent on time now. That's really the only change that you have to make. And you just go over here and put this in. And this is still going to be true. Because as time goes on now, थोड़ी देर बाद क्या होगा? थोड़ी देर बाद, well, थोड़ी देर बाद क्या होगा? मेरा duster गायब हो जाता है, लेकिन never mind. Okay, so you have, let me just remake the diagram. Okay, so you have A over here, P over here, B over here. And so you have this, this, this. Sometime later, according to A, sometime later, B might be over here. And then B would of course draw an arrow over here and A would draw an arrow over here. This is P, this is B, new position of B. A of course is still over here. Because ये सारी हमें diagrams हैं from the perspective of A. A कहेगा मैं उधर ही खड़ा हूँ, बाकी सारे move कर रहे हैं. ठीक है? So you again can see that this arrow plus this arrow is still equal to that arrow. Okay, so yes, these position vectors do change with time, but this relationship is always true. Okay, right? So the position vectors are essentially an observer dependent quantity. They depend on which observer you're talking about, who's performing the measurement. And the same is true for velocity. I already gave you a simple example in the beginning that there's a book stationary right next to you. You will say that the velocity of this book is 0. A person outside will say no, of course it's not 0. Okay, so let's see whether we can understand that. Okay, but before we see that, okay, before we try to formulate that, let me just give you a simple example. So for example, you have a car and you have another car and you have an observer on the ground. So there's a ground observer, this is a car observer A, and this is an observer B. So this is car A, this is car B. Okay, I tell you that the speed of car B is 80 kilometers per hour. What have I told you mathematically? How do I write that down? So this is a horizontal road. How do I write down the velocity of this car B then? No, how do I write down this velocity vector?
Speed of car B is 80.
Yes, 80 kilometers per hour.
Speed of car B.
आपने of course ये तो लिख दोगे, but then I said write down the velocity vector. So first of all, the first question now you have to ask is according to who? Not according to A. उसके जो भी आपकी गाड़ी की speedometer की reading होती है, that is always with respect to the ground. That is always with respect to a stationary ground observer. So this is the velocity of B according to observer G, who's stationary on the ground. And then of course this is not a vector. So you have to set up a coordinate system. G of course sets up a coordinate system with origin at his location. And then he sets up a unit vector like that. You just need one unit vector in this case because the cars are just moving horizontally. And then of course you just write that this is Ex. There you go. That's what the speedometer reading is telling you mathematically. That captures the full information. That the velocity of your car B according to the ground is equal to that. Whenever you say velocity, write down a vector. Okay. If I tell you that the velocity of car A is 50 kilometers per hour, how do you write that down? VAG equals 30 kilometers per hour. Again, with respect to the same coordinate system. If I now ask you, what's the velocity of B according to A? So you're essentially, I'm asking for you for this. What is the velocity vector of B according to A? I mean, that's why I am showing you this, okay? just to illustrate to you that that what you are doing is actually very simple things, except that we'll be considering them apply to more and more complicated scenarios. But it all goes back to whatever you do when you are trying to link velocity vectors in one frame to another frame, it all goes back to this. So why is it 50? Yeah, thank you. 80 minus 30 मुझे भी पता है 50 होता है, but so is 40 plus 10. Yeah, so with respect to according to the ground observer, he will say, well, in time t, if A and B started from the origin, in time t, B traveled a distance of 80t. In the same time, A traveled a distance of 30t. The distance between them is then 50t, and therefore the rate at which this distance is increasing is 50t divided by t, that is 50. Okay, so that's how you get 50 kilometers per hour as the rate at which the distance between them is increasing, which is nothing other than the velocity of B as measured by A. अब इसको हम विजुअलाइज करने की कोशिश करते हैं हो क्या रहा है. To measure the position vector of A, you draw this arrow. To measure the position vector of B, G draws this arrow. And then there's a third arrow that comes in, which is the position vector of B as measured by. So you very simply have that this yellow arrow equals the sum of this pink arrow and this. How do I describe this color? Okay, whatever. Okay. So anyway, so of this pinkish orangish color. Okay, whatever. Okay. So you have that these two arrows equals this yellow arrow, and that's exactly what you wrote down over here. That you have essentially over here. Don't memorize that. That's one very important lesson. Just very quickly draw the arrows and figure it out. Because in some other problem you might be dealing with, your friend has been thrown off a cliff. So then the object of interest would be, F. And then there's U. And then there's some other person in a moving car, for example. So there's the labels would be F, C and G probably. फिर आप लोग ये जितने ही आपके सीनियर कहे थे भाई ये मेमोराइज कर लेते थे, भाई कंफ्यूज रहते थे सर के वो नोटेशन में बी मूव कर रहा था या नहीं मूव कर रहा था, ए तो नहीं मूव कर रहा था, वो ऑब्जेक्ट जिसको स्टडी कर रहे तो पी था कौन सा था. ओके, सो जस्ट ड्रॉ इट अगेन. Okay, so essentially it's obvious from here that this yellow arrow, which is, let me just change colors, which is R BG equals R क्या? RAG plus, that's exactly the same as that. Okay, except that of course here the object of interest is B and the two observers are G and A. Okay. Now, if you say that, okay, that this is true at any time t, as we have already argued, this is true. And now I want to relate from this, I want to extract the relationship between the velocity vectors. What do I do? How do I find out the velocity vector experimentally of any object? अगर मैं कहूँ कि किसी भी ऑब्जेक्ट का वेलोसिटी वेक्टर निकालो, आप क्या करते हो? Exactly. You find essentially the position vector at two times that are very close to each other. So to measure the velocity vector of A, what will G do? Find out the position vector of A at some time t. Find out the position vector of A at time t plus delta t. Take the difference, divide that by delta t, that's your velocity vector. So you do exactly the same over here, except that this relationship is true at all times. Therefore, this relationship is also true at a short time later. In other words, if this is true at time t, you also have that plus, plus you have equals RAG E plus delta t plus RBA t plus delta t. This is true, as in this is true at a slightly later time. The relationship between these three arrows will still be that. And if you now take the difference of these two equations and then divide by delta t, what do you see on the left side? This thing minus this thing divided by delta t आपको क्या देगा? The velocity of what? Velocity of b according to g. Why? Because the position vectors that were used were the position vectors of b according to g, and therefore the velocity vector that you are talking about is the velocity vector of b according to g. So on the left hand side we will have that. On the right hand side you have this thing minus this thing divided by delta t. What's that? Velocity of a according to g, plus you have this thing minus this thing divided by delta t. What's that? There you go. And of course over here these velocities can be dependent on time. It could be that, for example, this car is accelerating, this car is also accelerating. Okay? Right? So that is your relationship between the velocity vectors.
Same relationship for acceleration.
Essentially, yes. Because if you look at it, what have I done? I've taken this equation and I've said essentially, look at the rate of change of this equation on both sides. If this vector is always equal to the sum of these two vectors, then the rate of change of this vector must be equal to the rate of change of the sum of these two vectors. Or in other words, what's the rate of change of this vector with respect to time, of course? Velocity. And you use the sum rule for derivatives, you get essentially the derivative of this plus the derivative of this. That's that. You differentiate this again, what do you get? The acceleration of b according to g equals the acceleration of a according to g plus the acceleration of b according to a. These are essentially your two fundamental relations that connect the velocity measurements according to one observer to the velocity measurements according to another observer. The acceleration measurements according to one observer to the acceleration measurements according to some other observer. Okay? And now for the rest of the lecture, the task of course is to get comfortable with these. Okay? Okay, so the first thing I need to do is to show you a video.
The demonstration of the independence of motion in the x and the y directions. What I have here is a cart that moves along the track and a ball with a plunger. And when I depress the plunger, then the ball is released and the plunger activates when this sensor passes a little metallic strip right here. So if the cart isn't moving, then the ball goes straight up and down and comes right back down to where it started. If I depress it again and give it a little bit of momentum, then what happens is the ball...
I'll show you that to you again, but essentially if you are in a train and you're standing in a moving train and you throw a ball straight up and the train is moving at uniform velocity, of course you should be able to catch the ball. The ball comes back to your hands, you threw it straight up, okay? But if you think about it, it's not as straightforward. If you think about it in the frame according to a ground observer, a very, very common mistake that people do is, oh well, according to ground, the person threw it up, and while the ball was up in the air, the person in the train, of course, went some distance forward. So the ball was left behind and fell behind that person. Of course, there can be no two ways about this. If you catch a ball, you win $1 million. For example, you know, that's how I've rigged the system, okay? So there can be no two ways about whether you win $1 million or not. if according to train observer, it cannot be that according to somebody in the train you won it, according to somebody outside you lost it. Okay, it cannot be such a situation. So according to the train according to somebody in the train, you threw it straight up, it came back down. That was analogous to what is happening over here. So right now, if the train doesn't move, of course, there's no confusion.
Then the ball goes straight up.
The ball goes straight up, comes back down.
Down to where it started.
Okay.
If I depress it again.
Now, if the train is moving, this viewpoint is, of course, according to somebody on the ground. You're looking at that moving train from the outside. You're looking at this moving cart. The ball has been thrown vertically with respect to the observer on the train. ट्रेन वाला बंदा कहेगा आपने सीधी बॉल ऊपर फेंकी थी. जो बैर बंदा खड़ा हुआ है वो कहेगा नहीं आपने सीधी ऊपर नहीं फेंकी, आपने आगे की तरफ भी फेंकी है थोड़ी सी. दैट इज बेसिक बट रिजॉल्व्स दिस कॉन्फ्लिक्ट के ओके आपने कैच किया है दोबारा या नहीं किया. बॉल आप वापस आपके हाथों में गिरती है क्योंकि बॉल को जब आपने थ्रो किया है ऊपर, व्हेन यू थ्रू द बॉल इनिशियली अपवर्ड्स, अकॉर्डिंग टू द ग्राउंड the horizontal velocity of the ball was not zero. It was actually nothing other than, as I'll show you very shortly, it was nothing other than the velocity of the train. Yes.
Sir, जो train वाला बंदा है उसने ball से ऊपर ही फेंकी है.
Yes.
Train की velocity है जो carry करेगी.
Exactly. Yes. So according to train observer, of course बैर वाला बंदा कहेगा नहीं उसने फेंकी ऊपर नहीं है, उसने फेंकी आगे की तरफ है थोड़ी सी. Yes. थ्रोइंग और ड्रॉपिंग में नहीं, इस केस में तो नहीं होना. क्यों? ड्रॉप अगर करोगे तो वो वेलोसिटी वो ट्रेन वाले ऑब्जर्वर के मुताबिक उसकी वेलोसिटी प्योरली वर्टिकली होगी. लेकिन जो बैर वाला कहेगा वो कहेगा नहीं आपने वर्टिकली ड्रॉप नहीं किया. वो एग्जैक्टली एज इन अगर आपने ये इधर रखा हुआ है कोई ऑब्जेक्ट, नीचे कोई प्रेशर पैड है जो कोई बॉम्ब से कनेक्टेड है, आप खुश हो जाओगे पहले मैं $1 मिलियन दिलवा रहा था. अगर आपने ये नीचे गिराई और वो प्रेशर पैड पे लग के बम ने फट जाना है, तो अगर ट्रेन वाला बंदा तो ऑब्वियसली कहेगा ये नीचे आपने तो मर जाना है. लेकिन बैर वाले बंदे को फिर वही कहना चाहिए. अगर बैर वाले बंदे को मुताबिक ये तिरछा नहीं जाएगा तो फिर कैसे लगेगा जाके प्रेशर पैड को. जो ट्रेन भी तो आगे जा रही है ना. ओके, सो नाउ यू हैव ऑल द मैथमेटिकल टूल्स टू एक्चुअली आंसर दिस क्वेश्चन. अब गौर से देखना वीडियो को. अनफॉर्चुनेटली इसमें जो है वो क्योंकि वो कार्ड की वेलोसिटी इतनी ज्यादा नहीं है, सो प्रॉब्ली यू नॉट एबल टू सी दैट क्लियरली, बट वॉच क्लोजली. जब ये मूव कर रही होगी द बॉल एक्चुअली फॉलोज अ पैराबोलिक पाथ, एंड द प्रॉब्लम फॉर यू नाउ, well actually I'll be solving it, so the problem for me would be to actually mathematically describe this parabolic shape. कि बैर वाले बंदे के मुताबिक ये पैराबोला की क्या शेप क्या है मैथमेटिकली. बट फर्स्ट देख लो पैराबोला गौर से, तो हल्का से पैराबोला बनता है. ओके, लेट्स सी हाउ दैट कम्स अबाउट. सो थिंक अबाउट दिस. ओके, दिस इज एब्सोल्युटली क्रूशियल फॉर यू टू अंडरस्टैंड न्यूटन्स लॉज. Without these, you won't be able to really understand what is going on when it comes to Newton's laws. Okay. So let's understand this now. As usual, जब भी आपने सर वो प्रॉब्लम को कैसे टैकल करना है, draw these diagrams. Without these diagrams, you won't be getting anywhere. Okay. Draw these very simple diagrams. ये एक ट्रेन बन गई. Okay. And don't waste time drawing these diagrams in the sense of कि कई दफा मैं ये देखता हूँ ये यूं बना देते लेकिन फिर यूं भी बना रहे होते हैं. हमें उसके बाल बनाने जरूरी है. Okay, so don't do that nonsense. कई जो smiley face भी बना रहे होते हैं. Okay, whatever. Okay, so don't waste time there. So this is a ground observer. अब कई लोग वो बड़े फिक्रमंद होते हैं, अच्छा ग्राउंड किधर रखना है, वो तो सामने से देख रहा है, आपने उसके पीछे बना दिया. It doesn't matter. Every ground observer will be stationary with respect to each other. तो उनके आपस में तो velocity कोई नहीं होनी. Okay, so the velocity of any object as measured by one observer on the ground will be exactly the same as the velocity measured of the same object by any other observer on the ground, because they are stationary with respect to each other. You can draw them wherever you like. Okay, it doesn't matter. Okay, so you have this ball. B और एक train observer इधर T. And now draw arrows. The train is moving. We are really interested in what happens in the situation according to the ground observer. Train में तो हमें फिर भी पता है कि भाई सीधी ऊपर जाएगी सीधी नीचे आएगी. Okay. So you have this, then you have this, and then you have a third arrow, which is this. This yellow arrow is क्या? Thank you. Yes. See, it's very straightforward. Okay. ये क्या arrow? White arrow क्या है? Yeah, very easy. Okay. और just consider कि arrow बनाया किधर से और किस तक बनाया. That's all it is. Okay. What's this yellow arrow? RTG. As the train moves, these arrows of course keep on changing. But the relationship between them is always true. You have this big yellow arrow equals this small yellow arrow plus this white arrow. Write it down. R at RBG equals RTG plus RBT. Again, don't memorize this. Always draw this diagram to actually visualize what's going on. और ये एक डायग्राम में बना दी फिर थोड़ी इसकी मूवी भी प्ले करने की कोशिश करो अपने दिमाग में. Of course, you won't be able to draw the movie, but you can imagine what's going to happen in the movie. Okay, बॉल ऊपर जा रहा है और ये ट्रेन मूव कर रही है and so on and so forth. Okay. Now I must point out कि again मैं फिर emphasize कर रहा हूँ कि इसको याद ना करना. A couple of years, I think 3 or 4 years ago, I think, तो वो illustrious batch जो है वो ग्रेजुएट कर चुका है. वो मैं देख रहा था कि they were able to do few of these simple questions at least without drawing any diagrams. और वो ये सही तरह लिख लेते थे. I was very curious कि भाई ये कैसे ये किधर से लिख दिया इन्होंने. डायग्राम तो कोई बनाई कोई नहीं. इनको कैसे पता कौन सा एरो किधर जा रहा है. पर फिर भी ये सही लिखी है इसने. उनसे पूछा मैंने भाई कि कैसे लिखी है. कहता सर मैं आपको बताता हूँ. Let me show you. Okay. So he said, okay, I don't think it was the same problem, but essentially, the same thing applies. So this vector equals this vector plus some other vector. आप देखिए जो भी इधर वेक्टर लिख रहे हैं ना, I can write this as BT plus RTG. और फिर ये देखिए दो सबस्क्रिप्ट मैच हो जाते हैं. वो एक दूसरे को एनाइलेट कर देते हैं और बाकी बच जाता है BG. और देखिए shockingly, it always seems to work, okay? Okay, but don't do that, okay? Okay, so you can choose that as a check कि आपने कोई गलती से कोई माइनस साइन की गलती तो नहीं कर दी, but make that proper diagram, okay? Okay. सारे पूछा सर ट्रिक क्या थी? Never mind, okay? Okay, you're seriously telling me आपसे 3 arrows नहीं बनते? Okay, so you have this, then you differentiate both sides and you get that. So whenever you have such a problem, 4 marks for example, you have probably already gotten 2 marks. तो इस कोर्स में कम से कम फेल तो नहीं होने लगे. If you are just able to show me that, okay, convince me of this, कि आपको कुछ पता है कि एरोज बनाए हैं एटलीस्ट के सही. Okay, now the person in the train observes that this ball is only moving vertically. उसने कोई coordinate system set up किया है which is moving along with the train, because the coordinate system according to the train observer should be stationary according to the train observer. वो उसका अपना ही coordinate system है ना. हर कोई कहता है कि मैं खुद रुका हुआ बाकी सारे move कर रहे हैं. Okay, so that means that I know something about VBT. Yeah. The train observer sets up a coordinate system in the train. वो कहता है ये मेरी y axis है. Now can you write down VBT? It's some number which can be changing with time, but it is only in the y direction. As in the vector is only in the y direction. That's what we mean mathematically when we say that the train observer says that the ball only travels vertically. That in the train coordinate system, the velocity vector of the ball only has a vertical component. Okay? देखो ये इतनी सिंपल सी बचगाना सी चीजें हैं. Okay? Anyway, पता नहीं क्यों इतने हैरान हो के क्यों देख रहे होते हैं, लेकिन सिंपल ही है. Okay? Okay. Now what else can I say? What can I say about VTG? अब आपको आ जानी चाहिए क्या? How do I describe mathematically VTG? The ground observer now sets up his coordinate system, of course. वो कहता है ये मेरा x axis है और ये मेरा y axis है. In terms of this coordinate system, what is VTG? The speed of the train times Ex. The train, we assume, is only moving horizontally. So you write down VTG is equal to VTEx. VT is just the speed of the train according to the ground observer. अगर आप चाहते हो इसको VTG कहेगा. Okay. ठीक है. I've only put in the additional information into this. I've just put in the additional information that the train is moving horizontally. But according to who? According to the ground. ट्रेन वाला ऑब्जर्वर कहेगा मैं तो आराम से बैठा हुआ, बाकी सारे मूव कर रहे हैं. वैसे आप एक ट्रेन में जा रहे हो, आप कहोगे मैं बैठा हूं, ये दरख्त पीछे की तरफ मूव कर रहे हैं. Of course, for biological reasons we don't say that, but physically you can say that. Okay? Right, so you have this, and now you can find out straight away what's the velocity of the ball according to the observer on the ground. VBG equals, all you have to do, so really relative velocity, relative acceleration, these relative position vectors, if you want to put it that way, is really nothing other than addition and subtraction of vectors. That's all it is. Okay, so anyway, so VBG equals this. इधर डाल दो, क्या आएगा आपके पास? VTGEX plus VBTEY. The velocity, the direction of motion of the ball, in other words, the direction of the velocity vector, remember, tells you about the direction of motion. The direction of motion of the ball has both a horizontal component and a vertical component. It's not moving straight up. It's really the same thing as this example that I did. ये जो 80 kilometers, 50 kilometers, 30 kilometers वाली जो थी. It's really only surprising because you are seeing the same thing applied in 2D. उधर सारे 1D vectors थे essentially. इधर 2-dimensional vectors थे. That's really why it's looking more complicated, although it's exactly the same thing. Okay? Now if I ask you, describe mathematically the trajectory of the ball as observed by the ground observer. Okay, ये चलो उससे भी simple. Suppose that चलो मैं आपको numbers दे देता हूँ. Suppose that the person in the train threw the ball up with a speed 5 meters per second, and the train is traveling at a speed of 5 meters per second. चलो 10 meters per second. Okay, just to make the numbers different. Okay, what does the ground observer initially see to be the direction of motion of the ball?
45 degrees.
How did you figure that out? In which direction is the ball initially moving according to the ground observer? So that actually contains a very important lesson for you. और ये गलती है जो हर कोई करता रहता है. The angle at which a projectile is launched depends on the reference frame. That's obvious from here. The angle at which the ball was thrown was 90 degrees with respect to the horizontal according to the train observer. That's what it means that I threw it vertically. But according to the ground observer, the ball was not thrown vertically. It was thrown at an angle smaller than 90 degrees with respect to the horizontal. बॉल आगे भी गया था, ऊपर भी गया था. So if I say that an archer shoots an arrow of with respect to the horizontal at an angle of 45 degrees, and then he gets on a horse and does the same thing, analyze the motion of the arrow, पूरी क्लास 45 डिग्रीज के एंगल को चेंज करना भूल जाती है. Because now the archer is shooting at an angle of 45 degrees with respect to the horse, not with respect to the ground. Okay? Anyway, so you have this. Okay. So of course this applies to any time. So in particular this applies to the initial time. So the velocity of the ball according to the ground just after the ball is thrown equals the velocity of the train according to the ground, that is constant because the train is moving at a constant speed, plus the initial velocity of the ball according to the train observer. So I said कि ये क्या है 10 meters per second, yes it's constant, 10 meters per second, and this is initially 5, of course that is what I meant by u. Of course this thing keeps on changing with time. The ball ऊपर जाता है नीचे आता है, of course this thing changes. Okay, so this thing initially is 10 ex plus 5 ey meters per second. Now can you tell me what angle does the ball make initially? I mean you're probably right, मतलब कि आपके करने का तरीका सही है, except that you forgot the tangent inverse half क्या होता है. Tangent inverse half क्या होता है? Okay, I think so, yes. Okay, anyway. So remember when I'm saying what's the direction of motion of the ball, whenever I talk about the direction of motion, आपने किस वेक्टर की बात कर रहे हो? Velocity vector यार, velocity vector tells you about the direction of motion. If you know the velocity vector of some object, you know where it's going to be some time later. You know how it's going to move, in which direction it's going to move. Okay, so I'm talking about the direction of the velocity vector. If I say sketch this velocity vector, that's what you have. कि ये जो है velocity vector जो है ये this is 10 and this is 5. That's this velocity vector. If I say what angle does this velocity vector make with the horizontal, कैसे निकालोगे वो? Tangent of theta is equal to 5 over 10, which is half. And so theta is tangent inverse of half. That's the angle that the person outside will see the ball to make with the horizontal. इसलिए तो parabola में जा रहा है. So essentially ये जो parabolic trajectory जो ball करेगा, the angle that this tangent line makes with the horizontal is tangent inverse of half. Okay, right. Now I ask you, find out the shape of this parabola. Mathematically describe the shape of this parabola. Okay, this is of course according to the ground frame. Ground वाला जो है अपना origin कहीं set करता है. Okay, for simplicity let's set it to be at the position where the ball was thrown. वो वाला point जो origin ground ने set किया है, remember that has to be remain at rest with respect to the ground. ये जो आपने origin ground वाले ने set किया है, that should not be moving along with the train. Train आगे निकल जाती है, वो वाला origin पीछे ही बैठा रहता है. Because that coordinate system, of course, the ground coordinate system, of course, has to be stationary with respect to the ground. That's what it means that you are performing measurements with respect to the ground. Okay, so you set up the coordinate system over here at the position from where the ball was thrown according to the ground. That the only reason why I've done that is to make the initial position vector of the ball according to the ground to be 0. You threw it from the origin. इससे तो मैं origin इधर रखा है. Okay. What's the initial velocity vector of the ball according to ground? Well, we know that. That is VTG EX plus UBT EY. Okay. What's the acceleration of the ball according to the ground? कौन सी? What's the acceleration of the ball according to the ground? उस पर फोर्स क्या लग रही है बॉल पे? माइनस जी ई वाई होगी ना, इतना क्या सोचने बैठ गए हो? ए बी जी इज इक्वल टू माइनस जी ई वाई, ये आपकी है, एंड दिस इज अ कांस्टेंट एक्सेलरेशन. So I can then figure out the position vector of the ball according to the ground because this is a constant acceleration. I can write down now. अब वो सारी पिछली इक्वेशन इस्तेमाल कर सकते हो. But now just keep in mind that you have to refer to किस ऑब्जेक्ट का position vector, वो तो आप already कर रहे थे if you had more than one object. But you also have to specify according to who. So the position vector of the ball B according to the ground observer at time t equals the position vector of the ball according to ground observer initially plus the initial velocity vector of the ball according to the ground times t plus half a t square. लेकिन a में क्या जाएगा? बदलो. मेक श्योर कि ये थ्रू आउट एक ही इस्तेमाल कर रहे हो. योर ऑल द मेजरमेंट्स विद रिस्पेक्ट वी हैव टू बी विद रिस्पेक्ट टू द सेम ऑब्जर्वर. ओके, नाउ यू जस्ट प्लग देम इन. ये तो जीरो है, प्लस यू बी टी आपका आ गया जी वी टी जी ई एक्स प्लस यू बी टी ई वाई टाइम्स टी माइनस हाफ जी टी स्क्वायर ई वाई. ये पहचाना? This is exactly the same position vector that you found for a parabola near flat ground, on flat ground, except उधर u cos theta को अगर आप v t g बना दो और u sin theta को आप u b t बना दो, you get exactly the same thing. In other words, the x coordinate of the ball according to the ground equals vtg times t. हॉरिजॉन्टली बॉल उसी तरह मूव कर रहा है जिससे ट्रेन मूव करती जा रही है. ट्रेन के साथ साथ मूव कर रहा है बॉल हॉरिजॉन्टली. वर्टिकली व्हाट इज हैपनिंग टू द बॉल इज ubt टाइम्स t माइनस हाफ gt स्क्वायर. अब पैराबोला नजर आ रहा है? ऑफ कोर्स नहीं नजर आ रहा. From here you can say that at any instant the time is linked to the x coordinate of the ball. This is equal to x bg divided by vtg. और अब ये आप इधर प्लग इन कर दो अगर, तो आता है आपके पास y bg equals u bt टाइम्स क्या t करना है ना, x bg divided by vtg माइनस हाफ जी था, जो मिटाने दो मुझे, माइनस हाफ जी टी स्क्वायर विच इज एक्स बी जी स्क्वायर डिवाइडेड बाई वी टी जी स्क्वायर. अब नजर आया पैराबोला? नहीं, ये y है, ये x है, ये x स्क्वायर्ड है. अब नजर आया पैराबोला? This is y equals some constant times x minus some constant times x squared. ये आपका vtg कांस्टेंट है, ubt कांस्टेंट है, g कांस्टेंट है, tg ये vtg स्क्वायर्ड कांस्टेंट है. यस, so this you are finding out कि ये जो पैराबोलिक ट्रेजेक्टरी बनी है according to the ground frame you have a parabolic trajectory. ठीक है? अगर आपसे कोई पूछता है कि भाई ट्रेन ज्यादा तेज चले तो ज्यादा पैराबोलिक ट्रेजेक्टरी आपको नजर आएगी, या ट्रेन आहिस्ता चले तो ज्यादा पैराबोला आपको नजर आएगा? You can ask all kinds of questions कि according to ground frame जो है वो फलाने पॉइंट के थ्रू गुजरती है बॉल या नहीं गुजरता, and so on and so forth. Okay, so in other words what I am looking for really is a mathematical description of this parabola. ये हम प्रोजेक्टाइल मोशन में ऑलरेडी कर चुके हैं. वो जो y is equal to tangent theta times x minus वो जो इक्वेशन लिखी थी. Okay, you're doing exactly the same thing over here. As in, this is saying that the y coordinate of the ball as measured by the ground observer at any instant of time equals the initial velocity of the ball according to the train divided by the velocity of the train according to the ground times the x coordinate of the ball according to the ground observer minus this thing. Okay, तो x is equal to 0 पे y क्या है? हाँ, ताकि you just get the dependence between x and y. आपका देखो जब x 0 है तो y 0 है. आपको प्रोजेक्टाइल इधर से शुरू हुआ था ना, and then it goes okay. अब बताओ अगर tg बहुत ज्यादा है तो फिर क्या होगा? If vtg is very very big, what do you see? इसके मुताबिक क्या आ रहा है आपका? Well, तो बिल्कुल हाँ, तो y is equal to 0 क्यों आया? y is equal to 0 तो x axis है ना, so why do you get that? फिजिकली सोचो क्या हो रहा है? अच्छा चलो लुक एट द ऑपोजिट. ओके, इसके बारे में सोचता vtg अगर 0 है तो फिर क्या हो रहा है? तो फिर बेसिकली यू गेटिंग y is equal to y becomes very which is equal to then which implies के आपका जो बॉल अकॉर्डिंग टू ग्राउंड ऑब्जर्व क्या किया उसने? स्पेस में नहीं गया. ओके, यू हैव टू लुक एट दिस, प्रॉपर लिमिट लो, ये वो लो, फिर आएगा आपके पास. ओके, सो एसेंशियली क्यों देखो मसला इधर ये हो रहा है आपके पास कि एक्स बी जी वो भी 0 हो रहा है. इफ द ट्रेन इज नॉट मूविंग एंड यू थ्रू द बॉल अपवर्ड्स, you threw it from xbg equals 0 और वो xbg 0 है तो 0 डिवाइड बाय 0 हो रहा है. इसकी इक्वेशन ब्रेक डाउन हो रही है. ओके, इस केस में. ओके, ओके, सो एनीवे, सो व्हाट यू डू हैव इज के you were able to translate a straight line motion. A straight line motion looks like a parabolic motion just if you go to a different frame of reference, and you should at least have some idea ke how do I mathematically do this translation. That was just an example of that. Okay, हाँ किधर? हाँ, yeah. So I set up the origin over there. ठीक है. Okay, now so just to simplify things, of course वो मैंने एक सिंपल सी आपको 2D में एग्जांपल कराई है, but just to bring the essential point home, for the next essential point home, let's go to a simple 1D situation. Okay, you have an elevator that's going up. According to who? According to somebody on the ground. A person within the elevator will say, well, I am stationary. The elevator is moving. I don't know. Okay, I am stationary. Okay. So there's a bolt on top of the elevator. There's a nail on top of the elevator, or something stuck to the ceiling of the elevator, and that gets loose and falls down. Okay. So essentially, this thing falls down. The height of the elevator is h. Okay. The elevator is moving up with constant velocity u. What's the time taken for the bolt to reach the floor of the elevator?
Relative velocity will be u minus ball
सोचो, ये तो सिंपल सा फिजिक्स का क्वेश्चन है. You have this elevator that is moving upwards with constant velocity. If there's a bolt, there's a nail or something stuck to the ceiling of the elevator that suddenly gets loose, and it falls down starting from rest. It falls down towards the floor of the elevator. The height of the elevator is h, as in the distance between the floor and the ceiling. What's the time taken for this thing to hit the floor of the elevator? Yeah, thank you. For the rest of you, make sure that you know how to do this. But आपने किस फ्रेम में किया ये? वो करने बैठ के बताओ, किस फ्रेम में किया था ये? लिफ्ट के अंदर वाले बंदे के मुताबिक कहेगा वो मैं स्टेशनरी हूं, वो बोल्ट नीचे स्टेशनरी है, बोल्ट ने डिस्टेंस नीचे फॉल करना है h. स्टार्ट फ्रॉम रेस्ट. ये तो सर मेरे ओ लेवल वाला है, x इज इक्वल टू यू टी प्लस हाफ ए टी स्क्वायर. x जो है वो h है, a जो है वो g है. देखे बल्ले बल्ले आ गया. ओके, दिस आई कैन डू. ओके, बट नाउ यू कैन नॉट इवन डू दिस. ओके, इतना मैंने दिमाग की पुटिया बना दी. ओके, एनीवे, बट नाउ somebody on the ground does the same calculation. जो बंदा बाहर बैठा हुआ है उसके मुताबिक बोल्ट की इनिशियल वेलोसिटी क्या है? u किस डायरेक्शन है? ऊपर की तरफ. So this object will actually move initially upwards according to ground observer. लेकिन वो नीचे क्यों आके गिर जाता है? क्योंकि वो ग्रेविटी उसकी वेलोसिटी नीचे की तरफ बना देगी बहुत ज्यादा. द एलिवेटर इज गोइंग अप. फिर वो कंफ्यूज होते हैं कि भाई सर ये टाइम से सेम तो नहीं आने लगा. सेम ही आएगा. द इवन दो द बोल्ट इज मूविंग अपवर्ड्स, according to the ground frame something else is also moving upwards, the floor of the elevator. वो तो भी तो उसी स्पीड से मूव कर रही है. एज इन वेरी सिंपली पुट, अगर मैं कहता हूं ये x is equal to 0 है at the instant where the bolt got loose, so I can write down के the elevator, the position of the floor of the elevator at time t equals that. What's the position of the bolt? This is equal to you set this equal to this, solve for t, you get square root 2h over g. Okay, just think about all this. Okay, ये अगली दफा करेंगे डिटेल में. Okay, but I'm just telling you in the rough steps. The final question is कि अगर एलिवेटर एक्सलरेट कर रही है फिर क्या होगा? इतना सिंपल नहीं है. इसके साथ लोगों ने कई साल स्ट्रगल किया था इस सिंपल से क्वेश्चन पे. आप लोगों ने बड़े आराम से कहते कि टाइम लगा देंगे साथ हो गए. यू इमीडिएटली रन इनटू पैराडॉक्स. जब एलिवेटर एक्सलरेट कर रही है, ग्राउंड के मुताबिक एक आंसर आता है, एलिवेटर बंदे के मुताबिक एक और आंसर आ जाता है. कौन सा सही है? सस्पेंस.